My name is Jim Jarvis, and the title of my presentation is 15K My Way. The objective of the presentation is just to share some tips and tricks that I've learned over the years that might help you succeed in launching a Mach Plus rocket to, say, 15,000 feet. Let me first introduce myself. As I say, my name is Jim Jarvis, and I live in Austin, Texas. I first became involved in model rocketry back in 1962, and I stayed with it until I got into high school. But I think it was an important factor that led me to pursue a degree in engineering. And in 1977, I got a degree in chemical engineering from the University of Wisconsin. I became a bar in 2003. I just happened to stumble on the Discovery Channel Rocket Challenge shows, and I was immediately hooked. I got my level 3 on the wonderful Animal Motor Works N4000 motor in 2007. I've been the vice president of the Austin area rocketry group since, probably for 10 years now, and my main responsibilities are to maintain the club equipment and to sponsor our monthly launches. And I'm also a member of the EEE TAP. There's a lot of things about rocketry that I like, but there's a few things that I like in particular. One of them is making carbon fiber rockets. And I started doing this, I think it was around 2005, when I had a particularly nasty shred and I decided that I needed to learn how to make stronger rockets. Another activity that I like is high altitude multi-stage rockets. I was honored to receive the NAR Science Award in 2013 for a flight that I did to 118,000 feet. I also like mentoring. I'm involved with most of the universities here in Texas, or many of the universities here in Texas, I should say. I've participated in the Student Launch Initiative a couple times and in the Spaceport America Cup a couple times, and I also do many of the NAR and TRA certifications at our local launches. And I'd say over the last 5 years, I've been involved in the development of a rocket stabilization system with a gentleman by the name of Dr. William Premerlani. I think I got the idea from a NAR Science presentation a few years ago, and this has been a whole lot of fun. The original idea was to place the stabilization system at this point on a multi-stage rocket. And the idea is that after the booster falls off, the stabilization system will bring the rocket back to vertical during the coast period, which is really important on a high altitude flight in order to land somewhere near the pad. And so the system does that stabilization and then falls off the rocket before the second stage ignites. I've also flown the system at the top of the rocket, both on single and multi-stage rockets, and it's starting to work pretty well. We've had some very successful flights over the last couple of years, and so I can't resist the temptation just to share one video of a flight. I think it was done about a year ago here, so let me get that up. So here we are prepping the rocket, and you can see the canards up at the top. This particular flight was on an L-1080 and went to about 8,000 feet. And the idea was to launch it at an angle, and then through the flight, watch it correct back to vertical, which it did. And the interesting thing about flying with vertical stabilization is that oftentimes when you get to apogee, the rocket will backslide, which is not something that you would normally expect to see. So the picture shows a 3-stage flight that I did a few years ago where I used the stabilization system. And the flight went to 175,000 feet, but the rocket landed less than 3 miles from the pad. I've really enjoyed the stabilization system, and I think it would make a great project for college rocketry teams just because of the different skills that are involved in doing it. So the title of my presentation is My Way to 15K, and is really intended just to share some ideas that people could use to fly more aggressive flights to 15,000 feet or maybe to 10,000 or 30,000 feet. So by way of agenda, some of the topics that I want to touch on first are fillets. If you're going to fly higher speed, maybe you want to use tip-to-tip reinforcement, and it's important to have a fillet that supports that construction technique. I'd also like to talk about zipperless couplers. I think they're a really good idea, and it surprises me how many people don't know what they are. So I wanted to talk a little bit about why it's a good idea to use zipperless couplers and some of the design techniques that you can use in constructing them. Then I'd like to talk about some design preferences that I have for altimeter bays and some of the things that I do on the upper airframe to try to make rockets stronger. And the last topic is a main deployment technique that I use. It isn't really anything that's associated with 15K per se, but I think it's a pretty good idea, and I've had success with it, and I'd like to go ahead and share it. So let's start with making a fillet. I think a couple criteria that I think are important are first is to have fillets that are pretty easy to make and that you can get through without taking a long time and having a lot of troubles making them. So we want them to be easy and fast. And then from a strength point of view, it's really important to have a large radius. I see a lot of tip-to-tip reinforcements where the angle is very sharp at the base and the tip-to-tip reinforcement is not really going to provide much strength in that case. So we want to use a large radius. So I put together a short video of making a fillet, and it'll go through just the steps that I use to do that. So let's go ahead and apply epoxy to this fin. Most people would be surprised. I use quite a large dowel to form the fillet. And the first thing that I'm going to do with it is to go ahead and score the fin and the airframe, just to use that as a guide for applying tape around the area where I want to put the epoxy. The size of the dowel depends on the airframe size. I'll typically go with a 1 1/8 inch dowel for a 3-inch airframe, maybe a 1 1/4 inch dowel for a 4-inch airframe. And I recall I did a 6-inch rocket once, and I think I used like about a 1 1/2 inch dowel for that. It's important to use a large dowel so that you have a nice round radius, because that'll improve the strength of the cloth that you're using for your tip-to-tip reinforcement. I think most people would also be surprised if they realize that I use laminating epoxy for making the entire rocket. I've never used structural epoxy, and the reason for that is I want to tailor the epoxy for the surface that I want. And in this case, the two additives that I'm going to use are called the West 404 high density filler and also the West 406 fumed silica. So those are the additives I'm going to use. But before I apply the additives, the first thing I do is I wet out the entire area where I'm going to put the fillet with unfilled epoxy. And I go ahead and I'm going to spread that out over the area where the epoxy is going to go. And it just sort of wets all the crevices and cracks because it's difficult to do once you produce the thick epoxy. So you want to start out by wetting the area where you're going to be applying the epoxy, and then basically removing all of that epoxy before you apply the filled epoxy. So here I've put in the high density filler, and then once that's mixed in, I'm going to go with the fumed silica. And the thing about the fumed silica is that it doesn't mix very well, and so you sort of have to take your stick and your cup and break up all the clumps to form a smooth mixture. And this might take, for a batch like this for a fillet, I might do this for 5 minutes just to to get everything mixed in there. And so I'm going to go ahead and put that in there. But I just want to say the reason that I use the fumed silica is it forms something called a thixotropic mixture, or a non-Newtonian fluid is another term for it. And what it means is that you can form the epoxy with your dowel, and the epoxy will shear and it won't pull it all away from the joint that you're trying to do. But then once you form it, if you form a radius, for example, the epoxy will basically thicken up at that point and it won't run. So you can form your radius with your stick and the epoxy will just stay there and it won't run off, and the epoxy won't settle. So the first thing I'm going to do with the stick is just to go ahead and hold it at a high angle and run it across the epoxy and just try to make sure that I don't have any voids in the epoxy. And this will remove most of the excess epoxy, but you're just trying to make sure that everything's filled in on the fillet before you actually go ahead and form the fillet itself. So you can see there I've uncovered a void, and so I'm going to go ahead and fill that in and make sure that everything is free of gaps. And now once I'm happy with that part of it, and I feel like I've got all the gaps filled in, I might go ahead and clean things up a little bit, but then I'm going to go ahead and I'm going to make the fillet, and I'm going to hold the dowel at a much shallower angle, maybe something between 30 degrees and 45 degrees. And you can see that the fillet is forming pretty easily. But once it's formed, it's not going to sag. It's just basically going to hold that shape. And you can move the airframe around, you can do whatever you want, and the epoxy won't move. So that's what makes fumed silica such a valuable additive. Now I'm just going to go ahead and do a little bit of touch up on the fillet and just make sure I got all the epoxy out of there that I don't want to be there. But you can see I'm not really doing much messing around with the fillet once it's formed. It's pretty much done right from the step. And if you look at the cross section, you can see that it really, even a large radius fillet doesn't really add that much epoxy to it. And it's real important for the strength of the fillet. The next area I'd like to talk about is zipperless couplers. I recommend using them, and I'll give you a few reasons here why I like them. If you decide to use them, there's some design choices that you need to make, and I'll present some of those alternatives. First, let me just go ahead and define what a zipperless coupler is. Basically, it just means that the coupler tube between the fin can and the upper airframe is glued into the top of the fin can. This is as opposed to many kits where the bottom of the altimeter bay is the coupler between the two tubes and the top of the fin can is just an open tube. So let's imagine that you're doing a flight and for whatever reason you have a significant horizontal velocity at apogee. So in this first drawing, this is right after the drogue deployment, and in this case the coupler tube is located in the upper airframe. So the first thing that happens is the upper airframe slows down because of the drogue, but the fin can continues to fly. And as it gets past the drogue chute and reaches the end of its harness, it has to make a 180-degree turn ultimately. And it's that turn with the harness acting against the top of the open tube on the fin can that causes the zipper to form. So that's the problem we're trying to solve with the zipperless coupler. So this third example shows the zipperless coupler installed in the fin can. And in this case, when the fin can has to make the 180-degree turn, the harness is acting against the top of the zipperless coupler as opposed to the top of an open tube, and that helps to avoid a zipper from forming. Now, many people like to attach the drogue chute closer to the upper airframe. I like to attach the drogue chute closer to the fin can. And the reason for that is as the fin can flies past the drogue, I want to keep that part of the harness shorter so that it can't collide with the upper airframe, which I've actually seen that happen. This drawing shows some alternatives for designing a zipperless coupler. All of the examples that I'm showing here use a piece of all thread which is connected to the forward closure of the motor and the top of the zipperless coupler itself to retain the motor in the fin can. You can either pull the motor up against the bottom of the zipperless coupler itself, or alternatively, you can hold everything together using the thrust ring at the bottom of the motor. In my zipperless couplers, I use multiple bulkheads, sometimes 2 and sometimes even 3. There's several reasons that I do this. In this first example, I'm using a U-bolt to connect the harness from the upper airframe, and I can attach the U-bolt to multiple bulkheads to reinforce the connection. An even more important reason to use multiple bulkheads is to help keep the coupler itself round. This part of the rocket with the tube brake is a weak point in the airframe, so keeping the coupler round using multiple bulkheads helps to prevent the coupler from deforming, and the result is a stronger airframe. This second example uses an I-bolt rather than a U-bolt for the harness connection. When you use this approach, you have to take steps to keep things from unscrewing while the rocket's falling under drogue. I use a nylon nut or a split washer and a nut at the I-nut location to keep the I-nut from unscrewing. But at the top of the forward closure, you can't use hardware to do that because something like a split washer or a nylon nut will just unscrew with very little force. Instead, you can use a cotter pin through the forward closure and the all thread so that the all thread can't come unscrewed. So this method is limited to forward closures with a stem where you can cut a cotter pin and insert a cotter pin into the closure. This example shows a design where the zipperless coupler is separated from the fin can, and this allows you to use motors of different lengths, and you just use the all thread in the motor to pull everything together. So this lets you use motors that are longer or shorter without being constrained by the initial design of the zipperless coupler. This last location shows how the motor can extend up into the zipperless coupler in the case of a non-minimum diameter rocket, and this can save some space. Like I said before, it always surprises me how many people are not aware of zipperless couplers and what they are. So I hope that those of you that may be in that situation will find the previous discussion useful. The next thing I'd like to talk about are a few issues around the altimeter bay and the upper airframe. I'm going to start out just talking about altimeter bays and a few preferences I have in the design of the bays that I use. Next, I want to talk about an idea where you just use a single airframe tube without any tube brakes for the upper airframe. Many airframes will use a tube brake around the altimeter bay or even 2 tube brakes if a switchband is used. And none of my rockets have tube brakes around the altimeter bay, and I think it improves the overall strength of the airframe, and so I wanted to talk a little bit about that. And the last thing I want to talk about is just some miscellaneous issues related to electronics around altimeter bays that might help you to make your flights more reliable or safer. This is one of my altimeter bays, and I'm not going to win any awards for it, but there's a few features that I'd like to point out. One thing to note is that I have a single piece of all thread that goes through the altimeter bay and holds the end caps on. This is opposed to eye bolts through either end cap and separate pieces of all thread that hold the caps onto the altimeter bay coupler. The advantage of this, in my opinion, is that the end caps themselves are no longer part of the structure of the rocket. And as I talked about with zipperless couplers, you can hold the eye nuts on either with nylon locking nuts or one or two split washers. The other thing you'll notice about the design is that I don't have any terminal strips external to the altimeter bay for the charges. Instead, I just run the E-match wire through the charge well, through the cap, and then down directly to the altimeter bay with no breaks in the wire along the way. And another thing to point out here is that I use a relatively thick piece of plywood as one of the end caps, and this is part of the structure that I use for holding the altimeter bay inside the airframe, and I'll talk about that shortly. The last thing I'd like to point out is that the altimeter bay doesn't have a switch band on it. Instead, I use screw switches located on the altimeter board itself, and I'll talk about that in a few minutes also. I do a lot of high-power staged flights, and one of the things that I've learned from that is that tube brakes can definitely reduce the strength of the airframe. So I'd like to make the case for trying to minimize the number of airframe brakes to the minimum possible. And one area where you can reduce either one or two tube brakes is around the altimeter bay. None of my rockets use tube brakes around the altimeter bay. Instead, I just have a continuous tube at that location, and then I just pin the altimeter bay into the airframe and avoid those tube brakes. So this is an example of one of my single tube upper airframes, and if you look at it, you can see a ring in the tube, and the altimeter bay simply slides down and sits on that ring, and then there's no tube brakes in the airframe. So since my altimeter bay doesn't have a switch band on it, there's a few things that I have to do a little bit differently. One thing is I have to mount the switches onto the altimeter board since there's no switch band to hold them. The switch that I particularly like to use is shown in the photograph, and it's called the Aerocon PCB switch. And there's two things I really like about it. One is that it's very simple. It only has one moving part, and that is the screw itself. The other thing I like about it is the screw is held tightly inside the body of the switch, and so it's very difficult for it to vibrate out. I've probably had over 100 of these switches, and I've never had a problem with a single one of them. Here's an example of how I use the screw switches. Somewhere near the edge of the altimeter board, there's a piece of wood with a hole in it, and I can just mount the switches in there. And what I'll do is solder the wire leads onto the back of the switch, and then mount the switch in the hole, and then basically pop the entire soldered area of the switch in epoxy so that there's nothing that can come loose or fail. Another thing that I have to do is to attach the altimeter bay to the airframe. And you can use screws for this or rivets, but the method I really like is to use socket screws. And these pictures sort of illustrate how it works. The first thing, I use a thicker piece of plywood as the base for the altimeter bay. And then you slide the bay into the airframe, and you use a drill to cut the hole both through the airframe and a little ways into the plywood for the head of the socket screw. And then you use a smaller drill bit to cut the hole for the screw part of the socket screw. And the thing about the fitting is that the socket head is tall enough so that it fits both through the airframe and also partway into the plywood. And because of the larger diameter of the head of the socket screw, it's very difficult to tear out of the airframe or the piece of plywood bulkhead on the altimeter bay. So here's what everything looks like once it's been assembled, and you can see the socket screws holding the altimeter bay into the airframe, and you can also see the holes in the airframe for access to the screw switches. One thing you can do to make installation of the socket screws easier is to use a drill with a pilot tip on it. The tip drills a pilot hole for the smaller screw to hold the screw part of the socket screw, and it makes the holes concentric, so it fits the socket screw, and you have a fair amount of precision doing that. I use 3 types of socket screws: 1/4 inch, number 10, and number 8. Most of the fittings I use are number 10s, and occasionally I'll use some number 8s. Here's just a few examples of how I use the socket screws. Basically, it's applicable anytime you want to mount something inside of a tube. And it turns out that at least on a 3-inch or maybe a 4-inch tube, you can submerge the socket screw just enough so that you can fit a tube over the top of it. So if you're mounting something inside of a coupler tube, you can set the socket screw so that an airframe tube will still go over the top of it, and that can be handy sometimes. The next area I want to talk about is some miscellaneous electronics approaches that I use that you might find handy to improve the safety or reliability of your flights. I do a lot of high-power staged flights, and one of the things that I don't particularly care for about when I do those is having to climb the ladder to arm the electronics. My opinion is that when you're on a ladder, you're in a vulnerable position, whether or not you're turning on a sustainer motor or whether or not it's just deployment charges. That's really not a good position to be in if you can avoid it. So one of the things that I've incorporated into most of my altimeter bays are Wi-Fi switches, and I really recommend using them. I use them with 1S LiPos. The manufacturer recommends 2S LiPos. But in either case, you can dump quite a bit of current through your altimeter with those kinds of batteries. So one of the things that I've increasingly done in my altimeter bays is to incorporate resistors in the circuit going to the E-matches, just to minimize the amount of current that's going to the E-match. And I do recommend that you look at your altimeters to see whether or not this is something that you need to do, or maybe you don't need to do it for some altimeters. I'm also just showing on the drawing the configuration, the wiring configuration that I like to use for staged flights. And you'll notice I have 2 switches on there. One is an igniter disconnect, and the other is a shunt. And shunts have to be designed, but I like to use them, and I think they're sort of like twisting the wire, I guess, but you do have to go through and do the calculations and the ground testing to make sure that they will do what you want them to do. I find putting a resistor in that part of the circuit also helps to reduce the total current that can go to the shunt and the igniter in case the altimeter fires inadvertently. And so I think a resistor, I also put resistors in that part of the circuit as well. One of the things that I've been doing more recently, and I notice a lot of the college teams are looking at doing this as well, but that is trying to make a shunt that can be removed from the ground so that, again, you don't have to be on the ladder at the point in time when you're doing the final arming of the sustainer. And here's just one example where I'm using a magnet that has a rope on it, and when everything is armed and ready to go, the last thing I can do is just pull the magnet off the airframe, and that opens the shunt switch, and then I'm ready to go. Another issue with the use of Wi-Fi switches is how to get the Wi-Fi signal out of your carbon fiber airframe. And a friend of mine who's an antenna expert recommended using a slot antenna. And it turns out that if you make a slot in your airframe that's about 6 centimeters long, that works out to about a half wavelength for the Wi-Fi switches, and it very nicely lets the Wi-Fi signals into and out of the airframe. The last topic in my presentation is the method that I use for deployment of the main chute that I'd like to just share. I developed it because I had problems when I was flying my stabilization system at the top of the rocket. And the problem was that it weighs a fair amount. And the result of that is that the upper airframe just always hangs straight down when it's time for the main to come out. And it seemed like no matter what drogue size I used, I couldn't get the rocket to fly in a V configuration to where the main would open out into clean air. But instead, it was always pointing down, and it would just follow the main, and I wouldn't get a good deployment. So I came up with this method, and I recognize that most of you are not going to be flying stabilization systems at the top of your rockets, but you might be flying payloads. That's certainly the case for many student projects, whether it's SLI or Spaceport. And the result of that, I think, is poor reliability for those projects as well, because the main will just foul in the airframe when it deploys. So here's the way I've configured my system. The lower part of it is basically just as I talked about before, with the zipperless coupler and with the drogue chute closer to the tin can section than the upper airframe. And on the left is the upper airframe, and the first component is a piston, and then there's two harnesses coming out from the piston. The first goes to the heavy nose cone. This would be the payload section or the stabilization section or whatever that's adding weight and causing the problem. The other harness goes to the deployment bag and the pilot chute. Now, I'm a big proponent of using pistons for the main section of the airframe. I think they dramatically improve the reliability of getting the main out. But in this configuration, you pretty much have to use a piston, because in a single harness configuration, the nose cone would pull the main out of the airframe. But since they're not connected in the case of the two harnesses, you kind of need a piston to pull everything or to push everything out of the airframe. So schematically, this is what we're trying to accomplish with the system. On the left is just the initial configuration with the upper airframe hanging straight down. The center picture shows what happens when the main charge goes off and both the nose cone and the pilot deployment bag deploy separately on their separate harnesses. And then in the right-hand picture, you can see that the pilot and deployment bag are starting to rise relative to the other pieces. And two things are important in this picture. The first is that the size of the pilot and the deployment bag is small relative to what a main chute would be. And this is what lets the pieces basically work their way up through all of the other pieces of the rocket without getting tangled. And the other thing to note is the main doesn't come out of the deployment bag right away. Rather, the opening or the separation of the deployment bag and the main are delayed. And that delay continues as the pilot chute and the deployment bag just continue to rise up relative to the other components of the rocket. Once the pilot and deployment bag basically are above everything else, only then does the harness pull tension and pull the main out of the deployment bag. But at this point, the parts are above everything, so there's no tangling of the main with the other parts of the rocket. So here's some photos showing how it actually works in real flights. The two pictures show again the upper airframe hanging more down than you'd like to have. And then here's what things look like after the main event occurs. On the left side, the pilot is already opened and it's starting to pull the deployment bag up relative to the other parts. On the center picture, the parts are still being blown away from the upper airframe as a part of the deployment. Now, a short time later, now you can see the deployment bag and the pilot are rising relative to the other parts, and here they're about even with the upper airframe. And that process continues, and at this point, the pilot and deployment bag are now basically even with the fin can and the drogue. Now you're just starting to pull tension with the upper airframe, and only now does the main get pulled out of the deployment bag. And you can see one of the things that's sort of interesting about this method is that everything is happening vertically. In some deployment bag methods, the bag gets pulled off and the chute sort of is oriented sideways. But in this case, everything is oriented vertically. And then the first thing that happens is the shroud lines get pulled out, and then the canopy. And you can see how nicely organized the shroud lines are here. And now when the canopy opens, it'll be in the correct orientation and above all of the other parts. And it's just a very reliable way to get the main chute open in the proper orientation. So I have just a couple more quick segments here. I should definitely thank the photographer, Harry Spears, for taking these great pictures, because they really have helped me figure out how this works. And this sequence is interesting because the rocket is literally coming right straight down on top of the photographer, and it really shows how the system works from below. This is a photo just showing some of the parts of the system. The deployment bags I use are just simply tubes closed off on one end, and there's no flap and there's no elastic bands for shock cords, and so the harness is attached to the pilot chute, and that goes through the deployment bag and then gets attached to the top of the main chute. And then the one thing I do is the shroud lines, I go ahead and I Z-fold those just to try to keep them organized. And then the harness from the piston would attach to the bottom of the shroud lines. And so when I pack this, I just roll up the main and put it into the bag, followed by the Z-folded shroud lines. And the idea is to try to get the main and the shroud lines to occupy about half of the bag. And then at that point, you just fold over the bag over onto the top of the main, and then I close the bag up with either 2 or 3 rubber bands. And this is real important because the rubber bands keep the deployment bag closed as it's flying under the pilot chute above all of the other parts of the rocket. So this is how I go about delaying the opening of the main chute until it pulls tension with the upper airframe. So here's the rest of the components of the system. On the left is the piston, and then you can see the 2 harnesses. And the harness on the bottom is the harness that goes to the nose cone payload section. And I go ahead and I Z-fold that part of the harness as well. And the idea is just to keep that part of the harness compact as long as possible after the main deployment, rather than forming just sort of a fog of harness that the deployment bag part of the system might tangle with. So I Z-fold that part. The upper harness is the part that goes to the main chute, the deployment bag, and the pilot chute. When I pack all of this, the order of it is important. Starting from the bottom, you have the E-bay, and then the piston, and then the first thing that gets packed is the harness to the deployment bag. And then the deployment bag and main chute sit on top of that, and then the pilot chute sits on top of the deployment bag, and then the last thing to get packed is the Z-folded harness that goes to the nose cone. So I hope you found that discussion of the deployment approach I used to be interesting. Other people have used it, and to the best of my knowledge, it has all been successful. The pictures show an example of a L3 certification flight that I tapped a few years back, where it worked just like it's supposed to. So I think at this point I have a few minutes left. So one last topic that I didn't have on the agenda, but that I'd like to share is the topic of fin adjustments. I adjust the span of my fins regularly on probably most of my rockets. One technique that I use is to initially build the rocket with a fin span that's larger than what I think I'm going to end up using. And then when the build is done, I can come back and weigh everything. And once I know where the center of gravity really is, I can go through and determine what the fin span will be. And then I just cut them to be at that span. And I also go the other direction. I have one rocket where I want to regularly adjust the stability of the rocket for different motors. So what I've done is cut the fin span down, and then I go ahead and I just add to it, just simply glue on a piece of basswood, or I've used balsa wood for this, and then I just sand them to shape. And when I get all done doing that, I'll just put a little bit of epoxy on there just to shine things up and harden up the wood. And I do this on pretty much every flight for this rocket, depending on what I want the stability of the rocket to be and for the motor that I'm flying. And I've done this on some pretty big rockets too. This was a fin tip that I added on to an aluminum fin can, and that was used on a P to N two-stage rocket a few years ago. And if you look on there, you can see where the fin tip was. And then you can see, here's a picture of the fin tab during flight. This was a picture from over Black Rock with the rocket traveling about Mach 1.5 at the time. So that's all I have for my presentation, and I thank everyone for watching and appreciate it. And if you have any questions, such as how the heck did Jim get that picture of that fin tip on that rocket, you're welcome to jump over to the 15K Q&A session, which will be starting right now.